Sometimes it's helpful, instead of doing Cartesian coordinates, as you know, it's easier to use polar coordinates. And you know, circular things come to mind, right? If I've got a, say my D area is a disk or a circle, i.e. is probably the best example we could come up with. All right, so that's what I'm going to call my area D. Okay. In Cartesian coordinates, okay, how would I do that? And let's say it's a radius 2 circle, centered at 0, 0. So these are 2, negative 2, all the way around, okay? Fairly complicated as far as x and y's are concerned. Well, one of them anyway. If I choose to go from down here to up here, okay? Well, I know it's a circle. So the equation, it's centered at 0, 0, radius 2. The equation is x squared plus y squared equals 4, right? And so if I'm going to go, and I can go across, but if I go from one y to the other y, I'm going to need a different format. I'm going to need the upper half and the lower half of that function, or that equation. So the upper half, if I solve for y here, I'd have y squared equals 4 minus x squared, and then I'd square root. So it's plus or minus the square root of 4 minus x squared. The top half is the positive square root of 4 minus x squared, and the lower half is minus the square root of 4 minus x squared. And so that's what my y's would go between if I did those first. I could do the x's first, but it'd be similar. So the point here is, you know, that the x's then would be not too bad, just negative 2 to 2. But the point is, let's think about it in polar coordinates. So that's Cartesian version of those x's and y's. What would polar be here? Well, to get polar, all I have to do is, remember, polar kind of sweeps out. We start maybe at the x-axis and then kind of just sweep out. We just have to go all the way around. So theta, I would just have to say theta goes from 0 to 2 pi. Remember, polar, you got r's and thetas. So just, yeah, we just sweep out theta from 0 to 2 pi. And then to get the whole thing covered, you know, I have to specify a radius. Well, the radius would just go from radius 0 out to the edge of the circle there. And so that's just r's going from 0 to 2. Now, which do you think would be nicer to work with in this particular case? Obviously, here we've got pretty complicated functions, and then here we just got numbers. So that's what we're talking about. This, if we could work with D instead in polar coordinates, you know, for circular things like that, that's going to be nice. And you know, it would even get better, you know, if I had instead of a solid circle there, what if I had radius 1 circle, this was radius 2 circle, and I just wanted that disk there. Well, you got a mess in Cartesian, I'll just tell you that, because I mean, you'd have to go from here to here, and then here to here. So you really have to set up two different Cartesian parts. But if we're doing polar, D here is still, I'm still going, theta is going 0 to 2 pi. And then R, like I said, R, this was radius 1, this was radius 2, so R is just going from 1 to 2 here instead, so. Much nicer. So sometimes it's just much nicer in polar. Is all the point of that is. Okay, so how do we do double integrals then in polar coordinates? And unfortunately, here is what we can't do. All right, so we've been working with these double integrals over area D, f of x, y, and then dA. Where dA is dy dx or dx dy. Unfortunately, no, you can't just do this. Okay. Doesn't quite, just switch them to r's and thetas and you're done with it, okay? Little more to it. Now what we can do, what we recall, remember what x and y are in terms of r's and thetas in polar? If we've got x, that can be set to what in r's and thetas? Wasn't it r times cosine theta? And then y was r times sine theta? Okay. And so you have to, a lot of times, use that, and that way you can switch over to it. So basically what this is saying is, so if you've got, there's a little more here that I'll have to do, but first thing to note is, yeah, I want to change, so I'll do f of r cosine theta for the x, and then y is going to be r sine theta. So that's the first thing. Now, the other thing is, what about dA? Well, unfortunately, dA, like I said, is not just dr d theta. It's close, but there's a slight little addition we have to do there. And just kind of go through it just to show you why, give you a little background there. Oh, the other thing here too, also sometimes on this conversion, x's are r cosine theta, y's are r sine theta. Sometimes too, remember, you can use, the goal is to go from x's and y's to r's and thetas, right? And so another, sometimes conversion that's helpful, sometimes you can use, make note here, the fact that x squared plus y squared is from Pythagorean theorem. X squared plus y squared equals r squared. So sometimes if you got x squared plus y squared, you can just change that directly right to, if you plug in this and this, you'll get there, but you can just go directly there if you remember that. Anyway, back to dA and dr d theta. Again, just kind of nothing else we're reviewing here. All right, so say we've got this polar region. They won't all be as nice as our first example there, just erased. But remember what you do in polar. All right, so let's say I've got this. All right, so this is R1 is some function of theta. I'm going to use h's here, whatever even. And then we've got another R2, and that equals h2 theta, some function of theta. So usually you want r's to be functions of thetas. And so what typically we do is talk about in an area D here that it's swept out. So we're sweeping out, going from this theta angle to that theta angle, and then R between the two. Anyway, where the conversion comes in here, talking about dA. So if I divide this up into how many ever parts, let's call this little part here, that's our little section of it. Because you know, just like you do delta x's, here you do delta thetas. And anyway, long story short here, you get this little piece here where this, of course, would be the change in the radius going from, that would be the change in the radius in the small increments. And then up here, that's an arc length. And remember, arc length, what you do is you take the radius times the angle. That's how you get that, which in this case, we'll just approximate it. Here it's r sub I, whatever the r sub I is, times the delta theta, whatever we're sweeping out there. So that arc length is that. And so that little piece, which is comparable sort of to dA, the area of that is, so, you know, it's not necessarily a rectangle, but that particular area, so delta A, we called it, approximately is this times that. So you got delta R times R sub I times delta theta. Which if you do, you know, more and more of the, make the increments smaller and smaller, the approximation becomes better and better. And then if you do infinitely many, here's what you get. Let's cut to the chase here. So we take, if we take small enough pieces, you remember it's kind of analogous to, you know, we talked about dy and delta y. Those two weren't exactly the same. They're approximately same thing here. If you do them small enough here, delta A is approximately equal to dA, delta R is approximately equal to dr, delta theta is approximately equal to d theta, if you do them small enough. And then if you do infinitely many of them, you get exactly dA equals, all right, so that'll be dr, r, and delta, d theta. So here's what the payoff is, what this means. What this means is when I try to get a volume this way and change it to polar coordinates, what I have to do for dA is do dr d theta, but it's got an extra r in it. So that's how you go from Cartesian to polar. You change the x's to r cosine theta, normally, and y's to r sine theta. Then you change it to dr d theta, but then you add an extra r, or multiply actually, an extra r. And then, okay. And this is typically the order you want, which is first, the r's. So that, just like we did here, usually what you want is you want the r's in terms of thetas, and that's what you're going to do first, and then your theta is your angle you sweep through. So anyway, shall we try one? Maybe two? Maybe three. All right. right, so the integral, double integral over d, 2xy dA, where d is the region in quadrant 1 between circles of radius 2 and 5. Centered at the origin. And so yeah, this one's one tailor-made for polar coordinates. So I want to go from the Cartesian setup here, because of my region being circles, let's change it over to to this polar again. Well, first of all, let's start. Let's get our polar values here. So I just want the quadrant 1 part of these circles. So that one's radius 2, this one's radius 5. So let's talk about this area here. Just the quadrant 1 part. So that means theta, well, the r's obviously are I'm going from a radius 2 to radius 5. So r goes between 2 and 5. What about theta? Well, I'm not sweeping out the whole 360 there, 2 pi. Theta would just go from 0 to 90, pi over 2. With me there? All right. So pretty nice. And again, if you think about doing this in Cartesian, we'd have to figure out, well, this is a function. This as a function, be a square root to this one. It's not going to be nearly as nice. That's what the point is. Okay. Now, back to this. All right. So what we saw was if I go to polar for this region, a couple of things. So what do I do with the x's? X's are r cosine theta. So this will be 2 times r cosine theta. Y's are r sine theta. And then what we saw was with our dA, the little extra part to it is, yeah, you're going to do dr d theta, but you need that extra, multiply by that extra r. So it's r dr. Okay, so we've converted to polar. And then my limits here. So we've already, like I said, we do the r's first. So it goes 2 to 5, and then theta is 0 pi over 2. That's what we got. Let's clean it up a little bit. What do we got? 2r cubed. Cosine theta, sine theta. Okay, so yeah, here's the, we can do that. Well, first point, if you've got just numbers, constants for your limits, and you can split the, what you're integrating up into, in this case, r's and thetas. Remember what we can do there? You can do them separately. As long, it doesn't work if these are, if one's a function of the other up here in the limits, but as long as you have constants here. So that's one point here. We can use that little trick. You don't have to, but you can. And here's what I'm going to do. So what that says is I can split them up, do the 2, let's do the 2 cosine theta, sine theta, d theta here. Whoops. Times the 2 to 5 r cubed dr. So as long as you've got those met, can do that. Here's the other thing. To do this, the little trick is, I guess it comes up a few times. Yeah, you can do that. Just leave it that way and I guess do U substitution. But another way to do it is, remember what 2 cosine theta sine theta equals. That actually equals, it's the double angle identity. 2 cosine theta sine theta is sine of 2 theta. I don't know that we've used that identity a whole lot, but might note that. So one way to do this, we could use U substitution, but another way, we're going to have to use U substitution again, but they like doing that. So I thought I'd show you at least one time doing that. Oops. Yeah, so then just so U equals 2 theta, du would be 2 d theta, so yeah, what you wind up having there is a half sine of U. Du, and that's just simply cosine. Antiderivative sign is negative cosine. That's negative 1/2 cosine U, but U is 2 theta, and so that's what we need to go back to, because then we're going 0 to 2 pi. 0 pi over 2, sorry. All right, then the other is just, that one's easy, because it's just power rule, so that's 1 b times 1/4 r to the 4th, and r is running 2 to 5, so plug those in, you got it. If we plug in pi over 2, that's going to cancel, so it's just negative 1/2 cosine of pi minus the negative 1/2 cosine of 0. And then times here, that'll be 1/4 of 5 to the 4th, 625. Times 1/4 times 16. Just multiply those two together. These turn out to be, that's 0, sorry, that's 1, or, sorry, negative 1. So you got negative 1/2 times negative 1, so you got a positive half. That's also positive half. So that's just 1. 625 over 4 minus 16 over 4, 609 over 4. Wait. I did something here. 609? Is that 609 over 4? Yeah, 609 over 4. Doubting myself there. All right. Here's another. Question on that one? Okay.